Welcome to the deep dive. Today we're diving headfirst into, well, a truly mind-bending journey through one of humanity's most groundbreaking scientific achievements.
We really are.
We're talking about a book whose very title, Relativity, the Special and General Theory, might make your brain itch a little bit, but trust us, even the author himself really went to great lengths to make it understandable.
That's right. Our source material for this deep dive is none other than Albert Einstein's 1924 revised edition of Relativity, the Special and General Theory.
The man himself.
Exactly. And Einstein was very upfront about it. He noted that despite its brevity, the book demands a fair amount of patience and force of will from the reader.
He didn't pull any punches there.
No. But he clearly stated he spared himself no pains in his endeavor to present the main ideas in the simplest and most intelligible form. He really tried.
And he even had that, delightful sense of humor about it, quoting the theoretical physicist L. Boltzmann.
Oh yeah, the Boltzmann quote.
Who famously said matters of elegance should be left to the tailor and to the cobbler, which really tells you, I think, that he prioritized understanding above all else.
Precisely. Clarity first. And that commitment to clarity is what we're going to rely on today.
Okay.
Our mission here is essentially to act as your guides, helping you extract the core ideas, the truly revolutionary aha moments, and maybe some surprising facts directly from Einstein's own words.
So we'll unpack how he just completely transformed our understanding of space, time, gravity, the universe itself, really.
The whole shebang.
Okay, so let's maybe start by setting the stage. What did the world look like, scientifically speaking, before Einstein dropped these bombshells? Most of us probably remember Euclid's geometry from school, right?
Yes, points, lines, planes.
All those seemingly unquestionable truths. But you're saying Einstein actually challenged the very notion of truth in pure geometry.
He absolutely did. What he argued is that pure geometry isn't really about physical truth in the real world. It's more about the logical connections between ideas. A statement in pure geometry is true if it's derived correctly from its axioms, its starting assumptions. But the truth of the axioms themselves, that's kind of meaningless within geometry itself.
So it's like a game with its own set of rules. The rules define what a straight line is, for example.
But you can't really ask if the rule itself is true in some absolute sense.
Okay. But where does that leave us when we try to apply these geometric ideas to our actual, messy universe? How does geometry become part of physics?
That's precisely the critical leap. Einstein says geometry only becomes a branch of physics when its propositions are applied to actual physical objects, things you can touch and measure, like practically rigid bodies.
Like a ruler.
Like a ruler, exactly.
Yeah.
Then, and only then, can you legitimately ask if those propositions are satisfied for those real things we have associated with the geometrical ideas.
So the geometry itself is abstract, but the moment you pick up that ruler and try to measure a physical line, suddenly the rules of that abstract game have real-world consequences.
That's it.
That makes a lot more sense. And when you apply geometry to the real world, you're defining positions using coordinate systems, like Cartesian coordinates, right?
Yeah.
X, Y, Z.
Right, the familiar grid. But even this seemingly straightforward concept needs careful handling, as Einstein points out.
How so?
Well, he gives us that classic example to illustrate this.
Okay.
Imagine you're inside a uniformly moving railway carriage and you drop a stone.
Okay.
To you, the observer in the carriage, that stone appears to fall in a simple straight line down to the floor.
But for a pedestrian standing on the embankment, watching the train go by, they'll see the stone fall in a parabolic curve, won't they? Because the train's moving forward as the stone falls down.
Exactly. And the fundamental takeaway here is pretty profound.
Hmm.
There is no single independently existing trajectory. There's no absolute space that everything moves through. Motion is always relative to a practically rigid body of reference or, a system of coordinates.
So space isn't this fixed, unchanging backdrop we thought it was. It's relative. Okay. And just to round out this classical picture, Einstein defines a Galilean system of coordinates. What's that?
That's basically any system where Newton's famous law of inertia holds true.
The whole body at rest stays at rest, body in motion stays in motion thing.
That's the one. Uniform motion in a straight line. Classical mechanics, as they understood it, was only considered valid for these specific Galilean systems.
It sounds like the universe was already getting a lot less straightforward than we might have thought, even before relativity really hit.
It truly was. And if that was just the warm-up act, well, buckle up, because Einstein is about to unleash the special theory of relativity. And he doesn't just poke holes in our understanding, he fundamentally rebuilds it.
Okay, bring it on. The first big idea here is what Einstein calls the principle of relativity in the restricted sense. What's that about?
This principle basically states that the laws of mechanics are the same in all those Galilean systems we just mentioned. If you're on a smoothly moving train, the laws of physics work just the same as if you were standing still.
Makes sense. But Einstein pushes this further, doesn't he? He argues it's a priori not very probable for a principle that works so well for mechanics to not apply to other things like light or electricity. Why extend it?
Well, he had this deep intuition, I think, that nature wouldn't be so arbitrary. If a fundamental principle holds true in one domain, like mechanics, why should it suddenly break down for other phenomena? It felt inconsistent.
Okay, a desire for universality.
Exactly. But this is where things get really intellectually challenging. Because this principle of relativity, which seems so natural, comes into apparent conflict with another foundational observation about the universe.
And that's the constancy of light's velocity, right?
Bingo. The observation is that light in empty space always travels at a constant velocity. See roughly 300 to 1,000 kilometers per second.
And crucially, this speed is independent of its color, or even how fast the thing emitting the light is moving. Astronomers like de Sitter had shown this with double stars.
Right. So here's the paradox. Imagine you send a ray of light along that railway carriage, moving at velocity v.
Okay.
Classical physics, the old way of adding velocities, would suggest that its speed relative to the embankment should be c plus v if it's going forward, or cv if it's going backward.
Just add the speed. Seems simple enough.
Seems simple, but it directly contradicts the observed constancy of c. Light is always measured at c, regardless of the observer or source motion. Einstein notes that this conflict plunged the conscientiously thoughtful physicist into the greatest intellectual difficulties.
I can imagine. So how do you solve that? One of these things has to give, either the principle of relativity or the constancy of light speed, or something else entirely.
And that's the genius move. To resolve this, Einstein did something truly radical. He re-examined the very definition of simultaneity.
Simultaneity. Things happening at the same time. Seems like such a basic concept, doesn't it?
It does. But what does it really mean for events happening at different locations? Say, two lightning flashes striking the railway track far apart. How do you know they happen at the same time?
Yeah, how do you know? You'd have to see them both.
Right. So Einstein proposes a precise definition. Two lightning flashes, say at points A and B on the rails, are simultaneous if light rays emitted from them meet at the exact midpoint m of the distance between A and B.
Okay, so if the light from both flashes arrives at the halfway point at the exact same instant, then we define the flashes as simultaneous.
Precisely. But what's absolutely crucial here, and Einstein emphasizes this, is that this isn't a supposition nor a hypothesis about how light actually behaves. It's a stipulation, a definition he chooses freely to arrive at a working concept of simultaneity.
So he's not discovering simultaneity in nature, he's defining it operationally in a way that lets the physics work out consistently.
Exactly. He's setting up the rules of the game so they make sense. This stipulation, this definition, then allows time to be precisely defined for various events relative to a specific reference body, like the embankment.
Okay, so time is now linked to this definition of simultaneity, relative to a reference body. Where does this lead?
This is where it really clicks. This leads to the truly revolutionary insight, the relativity of simultaneity. Meaning that if an observer on the embankment sees those two lightning flashes as simultaneous, because the light meets at their midpoint, an observer on that moving train will not see them as simultaneous.
Wait, really? Just because the train observer is moving? How?
Think about it. The train observer is moving towards one of the lightning strike points, say B, and away from the other A. Even if the light signals start at the same embankment time, the light from B has less distance to cover to reach the moving observer than the light from A does.
Because the observer is moving into one beam and away from the other.
Exactly. So the moving observer will see the flash from B before they see the flash from A. For them, the events are not simultaneous.
Wow. So the important result, as Einstein puts it, is events which are simultaneous with reference to the embankment are not simultaneous with respect to the train, and vice versa.
That's the bombshell.
Which means every reference body, coordinate system, has its own particular time. There's no universal now that everyone agrees on.
No absolute time. That's a fundamental challenge to centuries of thinking. It just blows the old Newtonian picture apart.
That is a huge shift in perspective. Okay, so simultaneity is relative, time is relative. What about space? Did that stay absolute?
Nope. Classical mechanics also tacitly assumed that space intervals, lengths, distances were absolute, independent of a reference body's motion. You measure a meter stick, it's a meter long, no matter how fast it's moving relative to you, or so they thought.
But that assumption had to go too.
It had to. Dropping both the assumption of absolute time and absolute space is precisely what resolves that nagging conflict between the principle of relativity and the constant speed of light. You need both to make it work.
So what's the mathematical machinery that makes this happen? How do you relate space and time coordinates between different moving frames while keeping t constant for everyone?
I think I've heard of the Lorentz transformation.
That's it. The Lorentz transformation is the mathematical heart of special relativity. It's the set of equations that tells you how measurements of space and time made by one observer relate to measurements made by another observer moving relative to the first.
And it's designed specifically to ensure that the speed of light key comes out the same in both systems.
Precisely. It's the mathematical rulebook that enforces light's constant speed. And the consequences of obeying this rulebook are, well, they're weird.
Weird how. What does the Lorentz transformation actually do to our measurements of space and time?
It leads directly to two famous counterintuitive effects, length contraction and time dilation. Okay, break those down for us. Length contraction.
It means that a rigid object, like a measuring rod, moving at a high speed, appears shorter in the direction of its motion when measured by a stationary observer compared to its length when it's at rest.
So a fast-moving spaceship would actually look squished from our perspective.
And the direction is traveling, yes. The faster it moves, the shorter it appears to become, approaching zero length as its speed approaches c.
Wow, okay. And time dilation.
Similarly, time itself slows down for moving objects relative to a stationary observer. A clock moving at high speed will tick more slowly than an identical clock that's at rest.
So astronauts on that fast spaceship would actually age slower than people back on Earth.
According to the stationary observer on Earth, yes. From the astronaut's perspective, their clock runs normally, but they see the Earth clocks running faster. It's all relative. And again, this effect becomes more pronounced as you approach the speed of light, c.
Which the theory says acts as an unattainable limiting velocity, right? Nothing with mass can actually reach c.
Correct. It would require infinite energy.
Okay, shrinking lengths, slowing time. This sounds like science fiction. Did Einstein have any actual proof for these wild ideas back then, or was it just elegant theory?
Oh, there was evidence. And fascinatingly, some of the strongest supporting evidence came from an experiment performed way back in 1851, over half a century before Einstein published Special Relativity.
An experiment from the 1850s confirmed Einstein. How?
It was by a French physicist named Fizeau. He was measuring the speed of light passing through moving water. Classical physics predicted one result based on simply adding the water's velocity to the light's velocity. But Fizeau's results were different.
Different how?
They perfectly matched the prediction made by relativity's modified velocity addition theorem, which comes directly from the Lorentz transformation. It wasn't the simple c plus v or cv.
So the experimental data was sitting there for decades, unexplained, until relativity came along and showed it made perfect sense.
Exactly. Fizeau's experiment, Einstein said, most elegantly confirmed the relativistic prediction. It was like finding an old treasure map that suddenly makes sense when you discover the key.
That's incredible. So besides solving this velocity addition puzzle, what was the broader impact, the sort of heuristic value of special relativity?
Well, first, as Einstein noted, it grew out of electrodynamics and optics, but it massively simplified the theoretical structure of physics. It reduced the number of independent assumptions needed to explain things.
Tidied things up.
Very much so. It also correctly predicted known effects on light coming from distant stars, like aberration, the apparent shift in a star's position due to Earth's motion, and the Doppler principle for light waves.
And crucially, didn't it also explain the behavior of electrons moving at high speeds? Things like cathode rays and beta rays from radioactive decay?
Yes, absolutely. Experiments show that the mass of these electrons seemed to increase as they sped up, approaching the speed of light. Classical physics couldn't explain this. Other physicists, like Lorentz himself, had tried to patch things up with ad hoc hypotheses, like suggesting electrons physically contract.
But relativity explained it naturally.
It explained it as a direct consequence of the Lorentz transformation and the relationship between energy and mass, which we haven't even gotten to yet with E-UY. But the theory accounted for the electron's behavior without needing any special tacked-on assumptions.
And it also explained the failure of experiments trying to find the ether, right? Like the famous Michelson-Morley experiment.
Precisely. For decades, physicists had assumed light needed a medium to travel through, this invisible, luminiferous ether. Experiments like Michelson and Morley's were designed to detect Earth's motion through this ether, but they consistently got a negative result. They couldn't detect any such motion.
Which was deeply puzzling.
Until special relativity came along and basically said, there is no ether. Light doesn't need a medium. The speed of light is constant for all observers, period. The theory elegantly explained why those experiments failed. They were looking for something that didn't exist, and the length contraction effect naturally accounted for the experimental setup's null result relative to the supposed ether wind.
So it didn't just add new ideas, it swept away old, unnecessary ones. Brilliant. Now, things get even more abstract with Minkowski, don't they? He introduced this idea of four-dimensional space, or the world.
Yes, Hermann Minkowski, one of Einstein's former teachers, actually. And Einstein mentions the mysterious shuddering many people feel when they hear four-dimensional.
Guilty as charged. What does it mean? Are we talking about extra physical dimensions?
Not in the way science fiction usually means it. Minkowski showed that the mathematics of special relativity becomes much simpler and more elegant if you treat time as a fourth dimension, alongside the three spatial dimensions, x, y, z.
So space and time are unified.
Unified into a single four-dimensional space-time continuum. An event isn't just located at a point in space, x, y, z, but at a point in space-time, x, y, z, t.
Okay, but how does treating time as a dimension help? He talks about using an imaginary time coordinate. What's that about?
The imaginary part is a clever mathematical trick. If you multiply the time coordinate t by the imaginary unit I, the square root of -1, and the speed of light c, you get a coordinate eta. When you do this, Minkowski showed that the Lorentz transformation, the thing relating measurements between moving observers mathematically, looks just like a rotation in this four-dimensional spacetime.
Like rotating an object in 3D space.
Exactly, analogous. And just like rotations in 3D space preserve the length of an object, these Lorentz rotations in 4D spacetime preserve a sort of distance or interval between events. This unification reveals a deeper structure. Physics, in this view, isn't just about things happening in space over time. It's about describing the existence of phenomena within this unified four-dimensional world.
Wow, okay. That's a lot to take in. So special relativity unified space and time for observers in uniform motion. But Einstein wasn't satisfied, was he? He wanted more.
He wanted to generalize. His next great ambition was the General Theory of Relativity, aiming to extend the principle of relativity to all bodies of reference, whatever may be their state of motion, not just those moving uniformly in a straight line. He wanted it to apply to accelerating frames, too.
And this is where gravity finally enters the picture in a big way, right?
Yeah.
How did Einstein think about gravity differently from Newton?
Newton saw gravity as a force acting instantaneously across distances. Earth just pulls the apple. Einstein, influenced by field theories and electromagnetism, thought differently. He describes the modern view. The Earth isn't just pulling the stone directly. Instead, Earth produces in its surrounding a gravitational field.
Like a magnetic field around a magnet.
Exactly, which acts on the stone and produces its motion of fall. The field is the intermediary.
Okay, so gravity is a field. And Einstein highlights a most remarkable property of this field, something we see every day but maybe don't think about.
He does. It's the fact that bodies, which are moving under the sole influence of a gravitational field, receive an acceleration, which does not in the least depend either on the material or on the physical state of the body.
Galileo dropping things from the Tower of Pisa, right? A heavy cannonball and a lighter musket ball hit the ground at the same time, if you ignore air resistance. Lead and wood fall identically in a vacuum.
Precisely. This independence from the body's nature is unique to gravity among forces.
And this leads to a key insight, doesn't it? The equality of two different kinds of mass.
Yes, the equality of inertial mass and gravitational mass.
Explain those quickly.
Okay. Inertial mass is a body's resistance to being accelerated. It's the m in Newton's Zephma. How hard is it to push? Gravitational mass, on the other hand, determines how strongly a body is affected by a gravitational field, how much gravitational charge it has, if you like. It's the m in Newton's law of gravitation.
And empirically, experimentally, these two completely different concepts of mass turn out to be exactly the same for any object.
To an astonishing degree of precision, yes. They are experimentally found to be equal. But in Newtonian physics, this equality is just a coincidence. There's no deep reason for it.
But Einstein saw a reason. He uses that powerful accelerated chest thought experiment. Walk us through that.
Imagine a physicist inside a large, windowless chest floating in empty space, far from any gravity. Now imagine a hook attaches to the top and starts pulling the chest upwards with a constant acceleration.
Okay, so the floor is accelerating towards the physicist's feet.
Right. The physicist feels pressed against the floor. If they drop an object, say a ball, the floor rushes up to meet it. From inside the chest, it looks exactly like the ball is falling downwards with constant acceleration.
Just like gravity.
Just like gravity. And crucially, if the physicist drops a lead ball and a wooden ball, they both fall to the floor at the same rate, because the floor is accelerating upwards equally towards both. Their inertial mass doesn't matter for this relative motion inside the accelerating chest.
So, the physicist inside the chest, unable to see outside, couldn't tell the difference between being uniformly accelerated in empty space and being at rest in a uniform gravitational field.
Exactly. Einstein argues that we must rather admit that his mode of grasping the situation violates neither reason nor known mechanical laws. This leads to the principle of equivalence. The effects of gravity are locally indistinguishable from the effects of acceleration.
And this equivalence explains why inertial and gravitational mass are equal.
It does. The thought experiment shows that the behavior we attribute to gravity, objects falling independent of mass, is perfectly mimicked by acceleration. Therefore, Einstein concludes, this extension of the principle of relativity to accelerated frames implies the necessity of the law of the equality of inertial and gravitational mass. It's no longer a coincidence, it's a consequence of this deeper principle.
Wow. So gravity isn't really a force in the Newtonian sense. It's somehow related to the geometry of space-time being affected by acceleration or mass. But does this mean all gravitational fields are just illusions, just apparent fields caused by choosing the wrong reference frame? Can we always just accelerate to make gravity go away?
That's a great question and an important clarification. No, not all gravitational fields can be transformed away completely. The accelerated chest example works for a uniform field. But real fields, like Earth's, are non-uniform. They point towards the center and get weaker further away. You can choose a freely falling reference frame, like an astronaut in orbit, where gravity seems to vanish locally right around you. But you can't find a single frame that makes Earth's entire gravitational field disappear everywhere.
Okay, so the equivalence is local. It connects gravity and acceleration, paving the way for curved spacetime.
Exactly. If acceleration can mimic gravity, and acceleration can be described by changing coordinate systems in spacetime, maybe gravity itself is a manifestation of the curvature of spacetime caused by mass and energy.
Mind blown again. Okay, this is general relativity. What was the proof? Did this radical new view make testable predictions? Einstein discusses three big ones. First, the curvature of light rays.
Yes. If gravity is curved spacetime, then even things without mass, like light rays, should follow these curves as they travel through a gravitational field. The theory predicted that light rays passing near a massive object, like the sun, should be bent.
Bent by how much?
Einstein calculated a specific amount, 1.7 seconds of arc for light, just grazing the edge of the sun. It's a tiny angle, but measurable.
And this implies that even the speed of light isn't quite constant anymore.
In a way, yes. The fundamental constancy is the speed of light in a vacuum far from any gravity. But within a gravitational field, the theory predicts light's path is bent, which means its effective velocity, as measured using the coordinates within that curved spacetime, can appear different. So, the constancy of the velocity of light in vacuo cannot claim any unlimited validity when strong gravity is present. Its coordinate speed can change.
Okay, a subtle but important point. How was this bending of starlight actually confirmed?
Famously, by Sir Arthur Eddington's expeditions during the solar eclipse of 1919.
The eclipse was key, right? To block out the sun's glare.
Exactly. They needed to photograph the stars very close to the sun's position in the sky. They took photos during the eclipse and compared them to photos of the same star field taken months earlier when the sun wasn't there.
And did the stars appear to shift?
They did. Expeditions to Sobral in Brazil and the island of Príncipe off West Africa both measured the deflection. The results were consistent with Einstein's prediction of 1.7 arc seconds. Interestingly, about half of that deflection could actually be accounted for by a simpler Newtonian gravity argument. But the full deflection required the space-time curvature of general relativity. It was a massive confirmation.
Incredible. Front page news around the world, wasn't it?
It made Einstein an international celebrity overnight.
Okay, what was the second big test?
Gravitational redshift. The theory predicts that time runs slower in stronger gravitational fields, or lower gravitational potential.
Like time dilation in special relativity, but now caused by gravity.
Precisely. Clocks deeper in a gravity well tick slower than clocks higher up. Einstein uses the analogy of a rotating disk. A clock on the edge moves faster and experiences a sort of artificial gravity outwards, and special relativity says it runs slower than a clock at the center. General relativity extends this to actual gravitational fields.
How does this affect light?
Well, atoms emit light at very specific frequencies like tiny clocks. An atom, Einstein writes, absorbs or emits light of a frequency which is dependent on the potential of the gravitational field in which it is situated. If an atom is in a strong gravitational field, low potential, its clock runs slower, so the light it emits will have a lower frequency shifted towards the red end of the spectrum compared to light from an identical atom in a weaker field, like here on Earth.
So light escaping from a massive star should look redder than expected.
Yes, a displacement towards the red, this gravitational redshift.
And was this observed?
It's a much smaller effect and harder to measure than the light bending, often masked by other effects like Doppler shifts from motion. But Einstein mentions it was definitely established by atoms in 1924 by observations on light from large stars, specifically the companion of Sirius. Later, more precise measurements confirmed it too.
Okay, 2 down. What was the third major confirmation? Something about Mercury.
Yes, the precession of the perihelion of Mercury.
Perihelion, that's the point in its orbit where it's closest to the sun.
That's right. Now, according to Newtonian gravity, Mercury's elliptical orbit shouldn't be perfectly fixed in space. It should slowly rotate, or precess, mainly due to the gravitational tugs of the other planets, especially Jupiter. Astronomers calculated this expected precession very carefully.
But the observed orbit...
Tiny, but undeniable. And it resisted all attempts at explanation within Newton's framework. People even proposed an unseen planet, Vulcan, orbiting closer to the Sun to explain it.
But general relativity had an answer.
It did. Einstein calculated the precession predicted by his theory based on the curvature of space-time near the Sun. On the basis of the General Theory of Relativity, he writes, it is found that the ellipse of every planet around the Sun must necessarily rotate. And for Mercury, the calculation yielded 0.43 seconds of arc per century, a result which is strictly in agreement with observation.
A perfect match. Out of the box, no Vulcan needed.
No Vulcan needed. This was perhaps the most stunning triumph for the theory initially, as it explained a known problem that had baffled astronomers.
3 big wins: bending of light, gravitational redshift, and Mercury's orbit. Solid evidence. Now let's get back to this idea of curved spacetime. How do we even describe geometry in a place that isn't flat, isn't Euclidean?
Einstein revisits that analogy of the heated marble slab. Remember, if you heat the center, measuring rods placed there expand.
Right, so you couldn't lay out a perfect grid of identical squares anymore. The geometry gets warped by the temperature difference.
Exactly. The physical conditions affect the geometry. And he says the same thing happens with gravity. The space-time continuum cannot be regarded as a Euclidean one in the presence of mass and energy. It's intrinsically curved, like that heated slab or the surface of a sphere. You can't just use standard Cartesian coordinates, x, y, z, t, in a simple way anymore.
So how do mathematicians and physicists describe these curved spaces? You mentioned Gaussian coordinates earlier.
Yes, Carl Friedrich Gauss developed methods for describing curved surfaces, like the Earth's surface, using arbitrary coordinate systems. Think about latitude and longitude on a globe. They aren't straight lines on a flat grid, but they allow us to label any point on the curved surface. General relativity uses a similar idea, employing these generalized Gaussian coordinates to map points in the four-dimensional curved space-time continuum. The key thing is that the coordinates themselves might not have direct physical meaning like distance north or time elapsed. They're more like arbitrary labels.
So what does have physical meaning then?
What's physically real are the events themselves and their relationships, like the encounter of two particles, or the emission and absorption of a light signal. These space-time coincidences are what the laws of physics ultimately describe, independent of the particular coordinate system you use to label them.
Einstein has another great analogy here, the reference mollusk. What's that about?
Yes, it's a vivid image. He imagines a sort of amorphous, non-rigid reference body like a mollusk spread throughout space-time. You could embed little clocks and measuring rods all over this floppy mollusk.
But the mollusk itself and the clocks and rods on it would be influenced by the gravitational field, right? They wouldn't be perfectly rigid or tick uniformly.
Exactly. That's the point. In general relativity, there are no truly rigid bodies or perfectly uniform clocks in a real gravitational field. So he uses this mollusk to represent an arbitrary, non-rigid frame of reference.
And the power of the theory is.
The great power of the general principle of relativity is that the fundamental laws of nature should take the same mathematical form, no matter which reference mollusk, which arbitrary coordinate system you use to describe them. All viewpoints, even squishy accelerating ones, are equally valid for expressing the laws of physics.
That's truly general. So gravitation isn't a force anymore. It's just the manifestation of space-time curvature, determined by mass and energy.
That's the heart of it. The theory of gravitation derived from the general principle of relativity, Einstein says, is not just beautiful, but it excels because it removes the defects of classical mechanics, like the need for action at a distance, and naturally interprets the equality of inertial and gravitational mass.
And Newton's theory isn't wrong, just incomplete.
It emerges as an excellent first approximation for weak gravitational fields and velocities, much slower than light. But general relativity provides the more accurate, deeper description, explaining the deviations Newton couldn't.
Okay, from the very small and very fast in special relativity to gravity and curved space-time in general relativity, what about the biggest picture, the universe as a whole? Did the theory have implications for cosmology?
Immense implications. Einstein points out that Newton's theory actually ran into serious trouble when trying to describe an infinite universe uniformly filled with stars.
Why trouble?
Well, calculations suggested that in such a universe, gravitational fields could become infinitely large, which seems physically nonsensical. Or, to avoid that, you might need to assume the universe has a center, which seems philosophically unappealing. Newton himself was bothered by this.
So how did general relativity offer a way out?
By introducing the possibility of a universe that is finite yet unbounded. This idea comes from non-Euclidean geometry, explored by mathematicians like Riemann and Helmholtz before Einstein.
Finite but unbounded.
That sounds contradictory. How does that work? He uses that analogy of the flat beings on a sphere, right?
Exactly. Imagine two-dimensional creatures living only on the surface of a perfect sphere. Their universe, the sphere's surface, has a finite area, right? You can measure it. But it has no edges, no boundaries. They could walk forever in one direction and eventually end up back where they started. Their universe is finite yet boundaryless.
And they could discover this geometrically.
Yes. If they drew very large circles, they'd find the ratio of the circumference to the radius is less than 2π, unlike in flat Euclidean geometry. That would tell them their 2D space is curved.
So Riemann extended this idea to 3 dimensions, a spherical space.
Riemann showed mathematically that a 3D space could be curved in a similar way, having a finite total volume but no boundaries. In such a space, straight lines, geodesics, would eventually loop back on themselves. Einstein poses the question, is our actual 3-dimensional universe infinite, as traditionally assumed, or could it be finite and quasi-spherical like this? And general relativity provides a link. How does the theory connect the shape of the universe to what's in it?
This is perhaps the most profound connection. General relativity says that the geometrical properties of space are not independent, but they are determined by matter.
Matter tells space how to curve.
And space tells matter how to move. That's the famous summary. Because there is matter and energy in the universe, gravitational fields exist. And this means space-time cannot be perfectly Euclidean or flat. It must be curved, at least locally.
So does the overall distribution of matter curve the entire universe?
Einstein argued yes. If matter is distributed roughly uniformly on the largest scales, then general relativity suggests the universe as a whole should have an overall curvature. And if the average density of matter is high enough, this curvature could be positive, like that sphere, meaning the universe would be necessarily finite, closed back on itself.
And the theory actually relates the size, the space expanse or radius of curvature directly to the average density of matter.
Yes, there's a mathematical relationship. More matter means stronger curvature, potentially a smaller, finite universe.
That's incredible. Matter dictates the ultimate fate and shape of the cosmos. But there was another twist, wasn't there? Expansion.
Yes. Initially, Einstein actually added an extra term, the cosmological constant, to his equations to allow for a static, finite universe, which seemed aesthetically pleasing at the time.
But then others looked at his original equation.
Right. In the 1920s, the Russian mathematician Alexander Friedmann showed that Einstein's original field equations, without the cosmological constant, naturally admitted solutions where the universe wasn't static. The world radius, the size of this potentially finite universe, could change over time.
It could expand or contract.
Exactly. The equations allowed for, even suggested, a dynamic universe, an expanding space.
And then came the observational evidence from Hubble.
Indeed. Edwin Hubble's observations in the late 1920s show that distant galaxies are moving away from us, and the farther away they are, the faster they recede. This was interpreted as the expansion of space itself, carrying the galaxies along with it. The spectral lines of light from these distant nebulae showed a redshift that increased with distance, evidence for this expansive motion of the system of stars in the large.
What a stunning confirmation of the dynamic solutions Friedman found. But Einstein, in his notes for the 1924 edition we're using, points out a problem even then, a strange difficulty.
Yes, even as the expansion was being confirmed, he noted a puzzle. If you extrapolated the observed expansion rate backwards, it suggested the expansion began only about 109 years ago, about 1 billion years.
And the problem was,
That time frame seemed too short. Physical astronomy at the time already suggested that individual stars and star systems were likely much older than that, having taken billions of years to form and evolve. So there's an apparent conflict between the age of the universe implied by its expansion and the age of the things in the universe.
so even as general relativity was explaining the universe's structure and dynamics, it was also throwing up new questions and inconsistencies to be resolved.
Absolutely. And that conflict, the Hubble tension, in modern terms regarding the expansion rate, is something cosmologists are still grappling with today, albeit with much refined numbers. It shows how scientific theories evolve, they solve problems, make predictions, and often uncover new puzzles.
Which brings us towards the end of our deep dive today. It's been quite a journey.
It really has, from questioning geometry to reshaping space and time.
We've journeyed through the real complexities of relativity, haven't we? Seeing how seemingly simple observations, like the constant speed of light or falling objects, could lead Einstein to these profound paradigm shifts.
And you really see his method, careful step-by-step reasoning, relying on thought experiments, but always demanding consistency and seeking unification.
You've witnessed how his revolutionary concepts allowed him to reinterpret the most fundamental aspects of reality.
It's quite incredible how Einstein didn't just present complex math, though the math is definitely there. He fundamentally challenged our basic concepts of space, time, and simultaneity. And by redefining those, he unlocked completely new insights into gravity and the very structure of the universe.
Yeah, it wasn't just equations, it was a new way of thinking about reality itself.
Absolutely.
And as we saw, while Einstein's theory predicted so much with, well, astounding accuracy bent starlight, Mercury's wobble, the expanding universe, it also opened up brand new questions, like that initial strange difficulty about the age of the universe suggested by Hubble's data.
Which continues to drive scientific exploration today. That's the mark of a truly great theory, isn't it? It doesn't just close doors, it opens new ones.
It leaves you with the understanding that the universe, in its very fabric, its structure woven from space, time, matter, and gravity, holds mysteries that these theories allow us to glimpse, inviting us really to keep asking questions and to keep exploring.